it decodes the signal that was encoded by the encoder. Okay, but can you rephrase it somewhat?
Decoder is the combination of output with the n inputs and 2 power n outputs.
Okay, Pallavi, yeah, answer. You can answer. So it has n inputs and 2 raised to n outputs. True. So basically, uh, okay, it converts an input to 2 raised to n outputs. Okay, that's true. So let's suppose we have uh, inputs a naught, this inputs given over here, a naught, a1, a2, a ray, a n minus 1. That is we have n inputs. The outputs that we get are 2 raised to n. What these 2 raised to n outputs represent? So for example, if I have just, let's say, a naught and a1, or let's say a1, a naught as my inputs, we just have 2 inputs, we will have 4 outputs, b naught, b1, b2, b3. So if we have 0 0 output, then the first bit should be high, rest all the bits would be 0. So it's like selecting one of the outputs, right? We change the input to 0 1, then the first select line or first output line would be activated 1 0, then the second line would be activated, third, last line would be activated. So this is basically a decoder. From this truth table, this is basically what we derived in the last slide. The 0 0 out inputs will activate the D naught bit, 1 0 will activate D1 bit, 1 1 will activate D2, and 1 1 will activate D3. So what we have is a combinational circuit where D naught is represented as AND operation between A naught and B naught. So we come up with the equations or expressions, logical operations between A and B to represent all 4 output lines D0, D1, D2 and D3. Apart from this, can we add another enable signal? So we have another 2x4 decoder. Here A, B, and we have one enable signal. D1, D1, D2, D3. So how this enable signal will affect our functioning of the circuit, and where should we modify all these changes that would happen in the digital circuit? We have just added one enable signal, right? So anyone? So just first let me know what is the purpose of including enable signal or using enable signals. It helps to enable the decoder. Okay. More descriptive. Can you be more descriptive? When decoder wants to perform, we give enable equal to 1. Okay, correct. So when enable would be 1, then only our decoder will perform the operations. Okay. So if we add another enable signal, we have to give it as 1 in order to have these outputs. When the enable signals is 0, then no matter what the inputs are, the output that we are going to get are 0, 0, 0 and 0. How do we modify the circuit? Or let's say, how do we modify the equations? Is there any term that is going to get added for D0, D1, D2 and D3?
Enable will add to the each equation.
Correct. So each equation will have enable signal and AND. So we will have another enable signal, and this enable would be added for each AND gate. We have modified equations as enable, enable, enable and enable. Is everyone with me till this point? Do anyone have any doubts? Doubts related to decoder? Should we proceed? Okay. So what we derived were the equations for D0 as Okay, so for D not, what we got was A bar, B bar enable. D1 was A, B bar enable. D2 is A bar B enable, and D3 was A B enable. So uh, can you guys let me know what would be the Verilog code for generating the circuit or generating this design? You can unmute yourselves and answer.
Input A B enable and the output D D not D1 D2 D3,
Okay.
and we can perform using case, or if we fails using
Fine. One way is doing for case. Okay, so let's start with writing the module decoder 224. We have input as A, comma B, comma enable, and output as D0, D1, D2, and D3. So first of all, just answer for structural modeling. Jignesh, no need to type each and every line for the code. You can just unmute yourself and answer. It would be much easier that way. Vignesh, sorry.
So we can assign the complement values of A bar and B bar by using NOT gate.
Right. So let's start off by defining some wires variable. Wire A bar and B bar. Then we have some NOT operations. NOT A bar A, NOT of B. Now can we directly start writing the AND gate? We have A bar, B bar enable, and output to be in D naught. Is this syntax correct?
no,
So
No.
first we need to write output, right?
Correct.
and we don't have instance names also.
So instance name would be given only when we have defined a module, right? The AND gate, NOT gates are predefined.
Primitives don't have instances.
No.
Okay.
So, and D naught A bar enable and D1 A D bar enable and A bar E enable and D3 A B enable. So this was which abstraction level?
Structural.
Right. So what would be the case when we want to design this using behavioral abstraction level? The inputs and outputs would remain the same. So what would be the inside logic?
Always primitive.
So,
Always. So,
can you repeat, please?
always procedural assignment. You can use it. Always rate of input.
Okay, always. Then
Then we can take case of A, B, and enable concatenation, and we can use 001, 101, 011, and 111 conditions. We can assign D naught value for the respective input.
correct. We can have always at the rate, and there is change in A, B, enable, begin, case, concatenation of enable A, B, begin, 3-bit binary 1 0 0, then D naught is 1, 3-bit 101. So is the code correct? Do we need any more modifications in the code?
Register.
Yeah.
Reg at the output side. Reg.
Where?
At output side, reg.
Okay, so output ports over here, right?
Yeah.
Correct.
And do combination have non-blocking?
You can, no issues. To be more precise, let's have equal to itself. Okay, what else? What else?
End case missed, I think.
Sorry, what?
End case.
End case, right?
Yeah.
What else? Let's say first my logic was my inputs were 0 0. So what happened?
Yes.
D naught became 1, right? Then in the second phase I gave input say as 1 1, then what would be the output?
Yeah.
Would it be D3? Right? So D3 output would be high, but we have never made our previous input as 0. So D0 would be still be 1. Did you guys understand? First,
Yes, we must for other conditions.
right. First, when my inputs were 0 0, then my output was D0. D0 equal to 1. Second time my inputs are 1 1. Now the output would be D3 equal to 1, but we never made D0 equal to 0, so D0 would also be 1. So our functionality fails. We have to add more statements, right? What can be those statements and where? Any answers?
D1, D2, D3 in for 1 conditions equal to 0.
Correct. D1, D2, D3 equal to 0. So similarly we have to write down for all of these, right?
Yes.
Correct. So any doubt in Verilog codes? Anyone? Anyone, any doubts? Should we proceed?
Hello, sir.
Yeah.
Sir, how can we find whether it is positive decoder or negative decoder?
Your voice is not clearly audible. Can you please write it in the chat box? Till then, anyone else has any doubts? Anyone else?
For default case, what would be
Sorry, what?
default case? What it how would if I'm
Defaults.
not mixed? Yes, sir.
Yeah, you can assign defaults as 0 0 0. You can write it over here. Veerbhadra, we will discuss it in the question sections. Okay? Don't worry, I have the same
Okay, sir.
questions. I have a question regarding the same. So for designing a higher order decoder from a lower order decoder. So suppose we have to design a 3x8 decoder from 2x4 decoder. Can you guys write down the truth table for 3x8 decoder? Then we will derive how we can use 2x4 decoders. for designing. So we will have 3 inputs, x, y, e, and outputs as d0, d1, d2, d3, d4, d5, d6, d7, d8. Just till d8, and I have my e over here. I don't have e this side. So 0, 0, 0, 1, rest all are 0. Yeah, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, and 1. So, is the truth table clear, or do you have any other alternatives or some other answers for the truth table? I hope you guys have came to the same truth table. So let's make division over here and division over here. Division again over here. So what we have done is basically we have segregated one of the outputs, E. Now this x and y for the first half, can we make this as one decoder, use it as a one decoder, and for other cases it's just 0, and for the second half we can use this as another set of decoder values. So isn't this quite similar to what we saw for 2x4 decoder with enable signals? So when the enable signal was 1, we get the outputs, and for the rest all cases where the enable signal is 0, we have outputs as zeros. So for enable equal to 1, we have the output of the decoder, and for when the enable was 0, we have all outputs as zeros. And the inverse, when the, let's say for this case we have to give it as enable bar, then all these would be 1, these all would be zeros. So for this decoder is giving the outputs based on the values of x and y, and for all the cases where enable was 0, enable bar is 0, sorry, the answers were negative, zeros. So for 2:4 decoder, the first decoder we have enable, and here we have as enable bar, and this over here enable, and the same set of inputs x and y can be given to these two decoders. Now, is this clear? First of all, just let me know if this design is clear.
Yes, sir.
Yes sir, okay, fine. So just let me know how can we just write down its Verilog code. Use structural modeling. So in structural modeling, what should we do? Should we write the get level structure, or should we write or use some instantiations? So instantiations, I mean use 2x4 decoder, instantiate it again and again where we need it.
You can instance 2x4 decoder we have written last time.
Correct. So for structural, for structural abstraction level, we will instantiate, and for data flow, we have to write gate level. Right. So I want the code for structural abstraction. So what we can do is write module decoder 3 to 8 inputs, outputs, reg. Now what we can have is a NOT operation of, let's say, e bar e, and then we can instantiate our previous design of decoder 2 to 4, where we'll be mapping the inputs dot we have a b enable. Okay, so we have dot a as input over here x, comma dot b as y, dot enable as, for the first decoder is e bar, dot outputs dot d naught would be d naught itself, dot d1 would be d1, goes on. And for the second decoders, for second instantiation decoder 2 to 4, again we will have same inputs a to x, comma dot b to y, comma enable. Now here enable would be connected to e, and all the outputs are now changed. From the d naught would be connected to d4, dot d1 would be connected to d5, dot d2 would be connected to d6, dot d3 would be connected to d7, and module. Is the code clear? Does anyone have any doubts in the code?
No, sir.
No? Okay, then let's proceed. Okay, this is the question. There is a design or the circuit given. You just have to find what it represents. Take 5 minutes and let me know the answer. I think no need of reg in output. True, because it's a combinational circuit, there is no need for reg as output, but it won't make a big difference.
Negative logic.
It's a 2 cross
Decoders,
4
sir.
decoder, sir.
2 cross 4 decoder, okay. So the first option, that the first answer that we have got is 2 cross 4 decoder. Any other answers?
Negative logic, sir.
Negative.
Logic.
Okay. Any other answers? Please everyone solve the question. Should we solve now? Anyone who have got answer other than these two answers? Anyone who has got the answer? Negative logic, 2 cross 4 decoder, okay. Two cross 4 decoder. So are you guys leaving something out? We have 3 inputs, right? A, B and C. So is there something that you are missing out?
So C is enabled, sir.
Okay. Okay, let's solve the question now. So we have three inputs, A, B and C, and four outputs, D0, let's say D0, D1, D2 and D3. Wires are defined as F, G and H, where F is nothing but A bar, G is nothing but B bar, H is nothing but C bar. So what we have first is D0 is written as F, that is A bar, B bar, C bar. D1 is written as A bar, B, C bar. D2 is A, B bar, C bar, and D3 is A, B, C bar. Correct? So now
Yes.
we have this very similar to that of a 2x4 decoder, right? 2x4 decoder. 0, 0, the conditions for 0, 0, 1, 0, 1, 1, 0 and 1, 1. So what, or let's start off by writing the truth table A, B, C, or let's have C over here, D0, D1, D2, D3, A 0, 0, 0, 1, 1, 0, 1, 1. For getting the output, what should be the value of C? It should be 0 or it should be 1?
0, sir.
0, correct. So 0, 0, 0, 0 and 0. And when it would be 1, the answers, it won't matter, right? It will all would be 0. So for in this case it would be 0, 1, 1, 1, 1, 1. Here it would be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Does everyone agree with this truth table? Oh, sorry. You should have pointed it earlier. It is written NAND gate. So what is D not equal to? So what is D naught? What is D naught?
A plus B plus C.
Sorry, what?
A plus B plus C.
A plus B plus C. Okay. True. let's have it in form of AND operations itself. So A bar into B bar into C bar whole bar.
Full bar.
D1 is equal to A bar B C bar whole bar. D2 is equal to A B bar C bar whole bar. D3 is equal to A B C bar whole bar. Now write down its truth table. A B C D0 D1 D2 and D3. So let's have 0 0 0, instead of 0 C 0 0 1 0 1 0 0 1 1 1 0 0 1 1 0 and 1 1. So for in case of 0, which would be active? Which output would be active?
D nuts.
So D0 would be definitely be 0. True?
D1, D2, D3 type.
Correct. D1, D2, D3. What about for the second case? Which outputs would be active?
D0, 1.
D0. Others?
0.
Sorry.
D1, 0.
This would be 0. This would be 1 and 1. For the next case, it will be 1 1 0 1. For this case, it would be 1 1 1 0. For all these cases, do all lines are 1? Now everybody agrees with this truth table? Everyone understands how we have reached to this truth table? Any doubts?
Sir, once again explain, sir.
Okay. So we have D0 value as A bar, B bar, C bar, whole bar. So when we have inputs at 0, 0 and 0, then we have in this values as 1, 1, 1, 1, which would be 1, and whole bar would be 0. So D0 would be 0 for the first case. What would be the value of D1? 0, A bar is 0, that becomes 1, B is 0, C bar 1, whole bar. So this becomes 0, whole bar, it becomes 1, right? So D1 is 1. Similarly for D2, we have 0, 1, 1, whole bar, which comes out to be 0 bar equal to 1. So D2 is also 1. Similarly D3 is also 1. Check for some other example. Let's say 0 1 0. For 0 1 0, what would be value of D0? A bar would be 1, B bar would be 0, C bar would be 1, whole bar. This is 0 bar, which comes out to be 1. So D0 would be 1. What about D1? A bar 1, B is 1, C bar 1 whole bar, it becomes 0. Did we make any mistake? Have we made any mistake in writing down? Why the answer is inverted? Any guesses? We are calculating it for this case. We want the value of D2. Let's say D2. What would be D2? 0. 0 all would be, this is again 0, C bar is 1, whole bar 0, 1. So D2 is 1. What? This value is 1. And this is coming out to be 0. And for, let's say for this case, what would be the value of D1? D1 would be 1, 0, 1 whole bar, that would be 0, 1. So this value is 1. This value would come out to be D2 is equal to 0, 0 bar 1. Are we making any kind of mistakes? Because I can't. Wait, that's. Anyone has reached to a solution or can figure out what is going wrong over here? Now calculate D1, D0. What would be D0? All are 1, 1, 1, 1, 1, whole bar 0. D1 as A bar D1, B 0, C bar 1, whole bar, it should come out 0 bar 1. D2 will come out to be D2 0 into D.
So as per the truth table, I'm getting 0, 1, 1, 1, and the next condition 4, 1, and next 1, 0, 1, 1, and 4 ones, 1, 1, 0, 1, 4 ones, 1, 1, 0, and 4 ones.
Can you repeat?
For 0, 0, 0, I'm getting 0, 1, 1.
Okay.
For 0, 0, 1, I'm getting 4 ones.
4 ones, okay.
And 0, 1, 0, I'm getting 1, 0, 1, 1.
1,
For 0 1 1 I am getting 4 ones,
Okay.
and 1 0 0 1 1 0 1,
1101. Okay.
and for 1 0 1 4 ones,
4 ones. Okay.
1 1 0 1 1
Sorry,
1
for 111
0.
you got.
Yes, sir.
Can you repeat the last one?
For 110 I'm 1110.
1110. Okay. And 111.
So that's correct. That's for the 101. The last condition is for 101. You are made 0 0. That one is for 101.
This is over here, and this is 0 1. Sorry.
Yeah. Then it should. Then its last one is 1.
All ones. What is the answer?
Yeah. For last for 111 4 ones.
4 ones. Okay.
Yeah.
This is for 110. It is all 4 ones, right?
For 110 1110. For 110 D3 is 0.
Okay, fine.
Yeah.
And for 101.
101 4 ones.
4 ones. So what would be the enable signal over here? Can you figure it out? What would be enable signal?
C is the enable signal, sir.
One more combination is missed. Writing.
Yeah. So till first 4 combinations are correct.
Yes.
What is for 100?
For 100 1101,
1101. Okay.
and next 101 4 ones,
4 ones. Okay. 110.
1110.
0.
Yeah.
Okay. Now are you guys sure that C would be the enable signal? Because I don't
Yes,
think
sir.
so. Oh, wait. Your C combination is over here or somewhere else. Have you written ABC or CAB?
ABC.
ABC.
Yeah.
Okay. Let's have ABC. Zero one zero one zero one zero one. Zero zero 10. Here. Yeah, so C is the enable signal. AB is 00 10. Okay, wait again. So I have to replace this entire table, right? So wait, keep C is over here. C is over here. 0 0 0 0 1 0 1 0 1. This is 0 1 0 0. This is 1 0 1. This is 1 1 0 1 1 1. All 4 now. So see this, and this. So we have this. Okay, now the truth table is correct. So we have C as enable signal and AB as 0 0 0 1 1 0 and 1 1. We are getting outputs as 0 for respective D0, D1, D2 and D3 elements. Right, so it is a negative logic with enable signal. Now anyone has any doubt? Everybody has got this truth table. If the truth table has been matched, then I think there won't be any issues in solving the question. Anybody who has not understand? Anyone? Should we proceed?
Yes, sir.
Okay. So I think someone also asked about the negative decoder, right? Veerbhadra. So have you understood what is a negative decoder?
Yes, sir. Understood, sir.
Okay, okay.
Yes, understood, sir.
Fine. So now this is the continuation of the last question itself, where we have replaced this AND gates with AND gates. So what would be the logic now? I think now
If we replace the NAND gate into AND gate, it will negative 2 cross 4 decoder, sir.
now it would be a positive decoder, right?
Yes, sir. Positive decoder, sir.
Yes. Now this would be a positive decoder. 2:4, right? Anybody, any doubts? Should we again draw the truth table and find out the answer? Does anyone find it difficult? Then we can do it. Should we find its truth table or should we go ahead?
Sir,
Yeah.
if we use the NAND gate means it is positive decoder, sir.
If we are using NAND gate, then we are getting a negative decoder, right?
Yes, sir.
So the outputs for which we should get 1, they are basically, the outputs are inverted when we are using NAND gates.
Okay.
Okay. So encoder, what is an encoder? What is encoder?
Two power n inputs and n outputs, sir.
Yeah, true. This is 2 raised to n outputs. We have n inputs and we have n outputs. So basically, it's just an inverse process of what a decoder performed, right? We had, let's say, 4 inputs: A1, A, let's say A3, A2, A1, A0, and this is B1 and B0. So if we have 0, 0, 0, 0, 0, let's say we have 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. Then this would be 0, 0, 0, 1, 1, 0, 1, 1. These are inputs, these are outputs. This is just this is just opposite what we did for decoder, right? We have a particular input coming as high in encoder and we are finding its respective output, encoded output. Based on this, can we find out the equations for B0 and B1? So B0 would be, when is B0 high? B0 is equal to A1 plus, let's say just A1 plus A3, and B1 is high when A2 plus A3, right? Is this clear?
Yes, sir.
Okay, now what about when I include a enable signal? Now what?
A plus A3 will end with the enable.
Correct. This will be enable.
And both.
So here also enable. This will be 1, 1, 1, 1. So what would happen if we are getting A3 and A2 both as 1 and 1, 0, 0? Is this case allowed?
It is allowed in priority encoder, sir.
It is allowed in
Priority encoder.
priority, okay.
A3 is selected because it has highest priority.
Okay. So this case is not basically allowed in a normal encoder. We have to avoid this case. But suppose for any application or some kind of errors, the two inputs are high. So what would be our approach in designing the encoder? In that case, we have to design a priority encoder. This D3 will have the highest priority, D0 would have lowest priority. Is this mandatory or can we change the priority? Can change. Yes, definitely we can change it. Suppose if I want to have D2 as my highest priority, then as D1, then D3, and last least priority to D0, can we design the circuit accordingly? Yes or no? If priorities is not fixed, then I can change the priority to any of the bits, right? I can have D2 as my highest priority, then D2, then D1, D3 or D0. Yeah, true. So can you guys just explain me this truth table? Just unmute yourself, any one of you, and let me know what this truth table means. Anyone?
Yes, this is a truth table for the priority encoder. Here the MSB is been prioritizing as per the truth table.
Okay.
Yeah, and during the first combinations for four zeros, the output will be don't care, and the valid signal is 0. And in second condition, the input combination is 1, and the output is 0 0, and it is valid condition. And in the third condition, I am either I get 1 0 or 1 1. The my output will be 0, only 1 0 1. That's a valid. And the next fourth condition, 0 1 XX. In this condition, the next four combination 1 followed with the 0 0 0 0 1 1 1 1 0 combination will have 1 0 as the output with the valid one.
Correct.
And the last condition will D3 1 D3 1 and XXXX will follow once the D3 will high, and the next 8 combination for the next 8 combinations, the output will be the 1 1 condition with the valid one.
Correct. So D3 has the highest priority, so the lower bits can be any of it. We don't care. Just because the D3 is 1, we will assign the outputs Y0 and Y1 as 1 and 1. When we are talking about D2, or let's say this condition, D2 has second priority, so it is mandatory that D3 becomes 0, D2 is 1, then we don't care about D1 and D0. The answer would be 1 and 0. So can you guys from this truth table derive these equations? Does y1 come out to be d2 plus d3 and y0 will come out to be d3 plus d2 bar d1? Can you guys verify these equations? are you guys able to verify these equations? Yes, good. What about others?
Yes, sir.
Okay, wonderful. So, can you guys write down the Verilog code for priority encoder? So what we had was y1 equal to what was y1?
B2 plus B3.
And what was y0?
B3 plus B1 into B2 bar.
b3 plus d2 bar,
Yes.
b3 plus d2 bar d1. So what are the Verilog codes? Module encoder 224 input d1 d2 d3 d4 and output y0 and y1. So we just wire d2 up, not not d2 bar comma d2, and we have assign y0 equal to, or let's have few more variables, a and b. Assign a equal to, or let's have and a comma d2 bar b1, and assign y0 equal to a plus b3, and assign y1 equal to d2 plus d3. So is this Verilog code correct? Any modifications?
Yes.
Correct. What about others? Any doubt till this point in decoders and encoders? Should we start with multiplexers if there are no doubts? Are there any doubts? Okay, wonderful. Okay. So, multiplexer. So, what is a multiplexer?
If then select line, we select the input.
Correct. Second question, what is the difference between an encoder and a multiplexer, or a decoder and a multiplexer?
No selective lines.
Okay. Some other answers?
Multiplexer has single output.
Fine. But what is the significance of that one output?
It can select the input. In the decoder, it only makes one. In the mux, we can give input 0 or 1. Just with select lines using select operation. We can select either 1 zeros. It can be taken either 1 or 0 based upon input combinations. But in the case of decoder, only it enables only one.
Okay. So the main difference is the inputs are directly connected to the outputs. If I0 input is selected, then the whatever the I0 value is there, it would be transferred to the output, right? So in decoder and encoder, there was no direct connection between the inputs and the outputs. Here we have a direct connection in multiplexers. So if we have a 2:1 mux, then this A is called as a select line or a controlled input. I0, I1 data inputs, Z would be the output. Raghunath, do you have any doubt? Raghunath. Okay. Fine. So if the select line is 0, then I0 would be selected. If it is 1, then I1 would be selected. Correct? So based on this equation, can we write the Verilog code for the multiplexer? Module mux 221 input as I0 I1 and output as Z. We have selected for A also. So can we have assign Z equal to not of A and I0 or oh sorry A is true, then what we can say is okay, let's have different abstraction levels. Gate level, how we can write gate level synthesis, what would be the equations or code for data flow modeling. You have to tell me two codes, one for data flow and second for behavioral. Any one of you would like to answer?
Not A and with I naught plus A and with I1 for data flow assign z equal to.
Correct. That's not of A and I naught A
Single
and I1. Correct. This
plus
is
plus.
for
Yes, sir.
and so this is for data flow, right? And what about behavioral?
Single and A.
What about behavioral? Assign Z.
For behavioral, we can use ternary condition.
A, then we can have input as I1 or I0. Is this code clear, both the codes? Are you guys familiar with this operator? Those who are not familiar, what we write first over here is a condition. Is a condition question mark. What is the statements when it is true, colon, when it is false, semicolon, end. Arvind, any doubts? Okay. The way in which we designed a decoder, right, from Arvind, is there any doubt? You are saying no for some reason.
No, sir.
Okay, fine. The way in which we designed decoder, 3:8 decoder from 2:4 decoder, can we have design of 4:1 mux using 2:1 mux?
3 mux we using, sir.
Sorry, what? 3 mux. Yeah, true. So we will have 3 mux. I0, I1, I2, I3, and this would be Z. The important question is what would be the select lines. If there are 4 inputs, then we need 2 select lines, right? So what would
It's
be the
not.
select lines?
It's not. This one. It's not for first 2 marks.
S0,
For first 2 marks.
and here
First
S1.
space. Yes, sir.
Correct. So can you write its Verilog code? Structure it. We have already written down for 2:1 mux in data flow and behavioral. Can we write 4:1 mux code using structure it? It's simple, right? Module mux 421 and 421 input I0, I1, I2, I3, S0, S1, outputs Z. So we can have module, mux 221 instantiation U0 dot I0 would be connected to I0 dot I1 would be connected to I1, I2 would be connected to I2 dot I3 would be connected to I3. Select line A would be connected to S0 and output dot Z would be connected to, let's define some wire, let's say A comma B would be connected to A. Again another instantiations mux 221 U1. Here I0 would be connected to, here I0 would be connected to I2 and I1 would be connected to I3 with select line connected to again to S0 and output would be connected to B. The third mux 221, here I0 would be connected to A, I1 would be connected to B, select line or dot A would be connected to S1 and output would be connected to output and end module. Is the code clear? And can you similarly write down the code for 8:1 mux using 2:1 mux? And can we have more hierarchy, like designing 8:1 mux, 8:1 mux using 4:1 mux and 4:1 mux by 2:1 mux. So we already have 2:1 mux. We have written the code for 4:1 mux. And can we use this module for making 8:1 mux? Again, we would have to use 3 4:1 muxes, right? And instantiating it in the similar way. Any doubts? Any doubts?
No, sir.
Okay.
No, sir.
So we have already written the Verilog codes. Can you guys solve this question?
2:1 mux. Select line as C.
Sorry, what?
2:1 mux.
Okay,
Select line as C. I0 as A.
2 is to 1
I1
mux.
as
And here the answers. Any other answers?
It's mux. 2:1 mux.
Okay, let's do the question. So P is nothing but naught of C. Then Q is written as PA, so that is C bar A, and R is written as BC, C into B. And finally output Y is given as Q plus R, that is A C bar plus BC. So this is the equation for 2:1 mux, right? Has everybody got the answer?
Yes, sir.
Okay, wonderful. What about others? Is there any doubt? Is there any doubt? Should we proceed?
Yes, sir.
Okay. So now coming to latches. So just a quick recap. What is the difference between latch and a flip-flop? What?
Enable signal will be used.
Sorry, what? What is the difference between latch and a flip-flop?
Flip-flops works on based on the edge. They are edge triggered, and latches are the lever triggers.
Correct. So the diagram that I have shown over here, is it a flip-flop or a latch?
Flip-flop.
Flip-flop. Anybody else? Is this a
Flip-flop,
flip-flop or
sir.
latch?
Flip-flop, sir.
Flip-flop. Okay. Any other answer? So nobody consider this as a latch?
Yes, this is a gated SR latch, right?
Gated SR latch, okay. Those who were saying the answer is a flip-flop, can you explain why it's a flip-flop? Anybody? Okay, we use clock, so it's a flip-flop. But even on the clock edges, right? A latch works on the level of the clock. So why this is a latch or why this is a flip-flop? Okay, let's start off by just looking at this part. Okay, let's say that this is A and this is B. Can anyone explain me the functionality of this part?
It works like a memory element.
Mm-hmm. Right. So anything else? See, let's have some conditions when A is equal to B equal to 0. So we have 0 over here, 0 over here. So if this is 0, then what can we say? Does this NAND gate will give us 0 or 1 as output? We definitely have 1 and 1 over here, right? Is it true? When we have 0 and 0 on these ports, we are getting 1 and 1. And do you guys have any other answer for this? See, if we have a NAND gate, then 0 0 0 1 1 0 1 1. So this would be the truth table for NAND gate, right? So if the output is one of the input is 0, then definitely the answer is 1. So both the Q and Q bars are held at 1, which is probably should not be the case. Is equal to 1 and should not happen. Let's change the condition. Let's have A as 1, B equal to 0. If now this is 1, then what could be the answer? If this is
0,
1,
1.
so B is 0, so the Q bar still remains at 1. Correct? So this one will go over here. 1 1 would be 0. So Q becomes 0. So Q is equal to 0, Q bar is equal to 1. Similarly, when we go for A equal to 0 and B equal to 1, then what would be the case? Now here
Equal
A
to
is
1.
equal to 0 and B is equal to 1. So when A is equal to 0, then definitely Q is 1.
Bar
So
is
if Q is 1, we have 1 over here, Q bar becomes 0. So Q is equal to 1 and Q bar is equal to 0. What is the case when A and B both are 1 and 1?
used.
Both are 1 and here is also 1. So what happens is, when both are 1, at one condition, what is the output? It is input negation, right? This is 1 and this is x, then we get x bar. So if we have input 1 over here, then we get q as q, right? So if we have q bar coming over here, it would get negated to give us q, and the q will go over here and we have a negation of it, so q bar will become q, q becomes q bar, and q bar becomes q. Oh sorry, q remains q and q bar is q bar. So it has hold its previous look, previous output. So this is a hold state. This is set, this is reset, and this becomes invalid state since q and q bar both can't be 1. So this is basically, now based on what the values of a and b, we have found out the conditions for q and q bar. Can we extend this circuit to get conditions on S, R and clock? So we already have 0 0 as invalid condition, 1 0 as reset, 0 1 as set, 1 1 as hold state. So this is basically when we are having a positive edge of clock. This is 1, this is 1, so we will have S bar over here and we have R bar over here, correct? So when S bar is equal to 0, when S bar equal to 0, then we have S bar, and R bar equal to 0, then we have invalid state. S bar equal to 1 and R bar equal to 0, then we have reset. S bar equal to 0 and R bar equal to 1, we have set, and S bar equal to 1 and R bar equal to 1, we have hold. So if we translate this, we can just write when S is equal to 1 and R is equal to 1, invalid. Reset when S is equal to 0 and R is equal to 1, S is equal to 1, R is equal to 0. Hold when S is equal to 0, R equal to 0, correct? So this is a SR latch. When S is high, output is set to 1. When reset or R is equal to 1, then output is resetted to 0. Is this clear? The entire operation of SR latch, gated SR latch. Do anyone have any doubts in the latch? Please let me know if anyone have any doubts in latch, functionality of a latch. Have you guys understood the latch? Any doubts in today's entire session? Okay. So we are already, the time is over, so it's 6:06. So we'll stop here for today. Next session, next Sunday, we would be continuing latches and flip-flops. It's Verilog codes, both on data flow and behavioral logics. Okay. So if you guys have no doubt in today's session, then I think we can close the meeting. No doubts?
Yes, no doubt.
Okay, then thank you so much for attending.
Thank you.